Hello everyone, my name is Yueying, and I'm a grad student from Carnegie Mellon University, and I work with Tiziana Di Matteo. And here's the list of members in our team. And today I'm going to talk a bit about the BlueTides simulation, the cosmological simulation that focus on the first generation of galaxies and quasars at the early universe. So here, this is a schematic timeline of the history of the universe. So when we are looking to the distance of the universe, we are basically looking at more and more distant objects residing in the early universe. So in cosmology context, we call them in the high redshift universe. So the time era that the BlueTides simulation focuses on is called the reionization era. This is when the first generation of galaxies and the quasars form, and the light from them start to heat and ionize the neutral hydrogen in the universe and start to illuminate the dark age ever since the Big Bang. And so our current observation has already been able to peek into this epoch. And however, it's still a largely unexplored frontier where we need simulation to help us to understand what's going on and make predictions for the current and future surveys. So here I introduce a bit our current state we have on high redshift universe. So our current observation on high redshift galaxies is actually quite limited. Here's a bunch of images we get from the Hubble Ultra Deep Field. This is they are very faint and clumpy objects that we obtained from staring at a small patch of the sky deep enough. And so our current observation is limited by the small volume of the survey. To give you a sense of how small the Hubble Ultra Deep Field is, we make it in comparison with the survey volume we do for the local galaxies. This is brought by the Sloan Digital Survey in our local galaxy. So here, every tiny point there's represent a galaxy here. So the effective volume we do for the local galaxies is like 200,000 times larger than the effective volume we probe to the high redshift universe. However, on the other side, when we are searching for the high redshift luminous quasars, we cannot do this by peeking into a tiny volume, tiny patch of the sky, because the high redshift luminous quasars are extremely rare. This is a plot of the number density of those luminous quasars as a function of redshift. We see that the number density declines rapidly when going to higher redshift. So at redshift larger than 6, basically we only can find one quasar out of a gigaparsec cube volume. So again, to give a sense of how rare it is, we compare it in the Sloan Digital Survey for the local galaxy. So in this comparatively large volume, we can only find 2 quasars up there by this number density estimation. Therefore, people need to search for the wide area in the sky to hunting for those extremely rare objects. And actually, we are making really rapid progress these days. In the last year, there are about 30 new quasars at redshift larger than 6.5 is discovered, and 3 of them are at redshift larger than 7. So here we plot all the quasars we know nowadays in their redshift and their UV magnitude, their luminosity. So we see that the black dots are the quasars known before, and the red dots are the newly discovered quasar in the last year. So we are really in an epoch of rapid progress in peaking to high redshift quasars. And what's exciting is that our ongoing BlueTides 3 simulation is going to cover this period and make more comparison with the new discovery of quasars, and also make predictions for the underlying physics there. And what is more exciting is that in the very near future, we're going to have even more rapid observation buildup of the observation data, because the next generation telescopes were able to bring us about 1,000 times more data at redshift larger than 7. So we are really in a regime that we need the simulation to give predictions for those future telescopes. So BlueTides simulation is such kind of simulation. The uniqueness of BlueTides is that it both covered a large volume of the universe, so that we are able to hunt for those really rare objects. And on the other side, BlueTides simulation is also capable of maintaining a relatively high resolution, so that we can resolve to those faint galaxies that is marginally detectable by the current and future observations. So we can develop a large ensemble of objects, a full spectrum of the objects that we are going to see by the current and future observation. And we can study them on a statistic basis. So the grand challenge here is that we need to cross over the a huge dynamic range. We know that the high redshift quasars are extremely rare. So the spatial scale we need to study those objects is many orders of magnitude larger than the scale we need to resolve to study those underlying physics, like the accretion, the feedback, the star formation, etc. And however, the information on all those scales are needed simultaneously, so that we are able to fully understand the underlying physics going on there, like how the quasars are grow and how do they dump feedback to the local environment and how do they co-evolve with their host galaxies. So to bridge over this huge dynamic range, basically we need a lot of particles and a lot of memories, which can only be brought by BlueWater. So BlueTides is a near full machine run that we use 20,000 nodes simultaneously to simulate over these close to 1 trillion particles on the 400 megaparsec large box. And we're doing this in the full hydrodynamic simulation. And BlueTides simulation is based on the code named MP-Gadget, massively parallel gadget. This is based on the very popular cosmological simulation code Gadget, which is using, it's a particle-based code. Here's the underlying physics here that we use the 3PM method to solve for the gravity and use hydrodynamics to model the evolution of the Barnett gas. And also we have a bunch of add-on subgrid physics that model the cooling and heating of the gas, the formation of the stars, and the feedback from the black holes and the supernovae, and also the formation of molecules and the metal enrichment, etc. So to make this code to be able to scale on the full machine of BlueWater, we need to make a huge improvement on the efficiency and the scalability of the code. So here is a comparison of the time used in each time step that MP-Gadget able to achieve comparing to the original P-Gadget 3 code. So we indeed able to make a lot of improvement in many aspects. Like we're able to get a more efficient long-range solver for the gravities, and we are also have improvement in short-range solver and domain decomposition. We are also have a very efficient binary to do the I/O output. We can output the 50 terabyte full snapshot in 5 minutes, so that we can do checkpoints very often. So here comes the full and the entire field view of the BlueTides simulation. We are able to form like more than 200,000 galaxies. It's a huge ensemble of galaxies which covers the volume hundreds times larger than the current observation get. So we can study those objects in a statistic basis. So here, as the first validation, we compare the luminosity function in the BlueTides simulation with the current observation data. As we mentioned before, that our observation is not very much, but with what we have, our galaxy luminosity prediction is quite consistent with the observation. So galaxy luminosity is basically the number density of galaxies sorted by the luminosity bins. And the blue lines are the predictions from BlueTides, and those black dots are the constraints from the observation. So this gives us a solid foundation that we are able to make further predictions for the future telescopes. So I'm going to focus a bit on the black holes, on the supermassive black holes formed in the BlueTides simulation. So after simulate over this huge volume, 400 megaparsec side box, are we able to find those extremely rare objects that catched by the current observation? So fortunately, we find them. the current record holder of the from the simulation of the highest quasar is a quasar resides at redshift 7.5. So they are so massive and luminous that we can see them this far away. And here is the entire population of the black hole in the BlueTides simulation at redshift 7.5. We see that on tip of this, the x-axis is their luminosity and the y-axis is their mass. So we see that on tip of this huge ensemble of iceberg, we finally got one such champion, the most massive black hole that has the mass and the luminosity comparable to the current record-breaking observation quasar. This is quite exciting. So we are going to explore its local environment, and also we make predictions for their host galaxies, which can be probed by the further JWST survey. So here's the mock image of the host galaxy and the mock spectra detected in different JWST filter band. So the takeaway message is that the host galaxy, which can be obtained by can be detected by the JWST survey, is super tiny and compact. So to give a sense of how tiny and compact it is, we make comparison of the host galaxy for our most massive black hole with the host galaxy for another supermassive black hole at the local universe. So both black holes have the same order of black hole mass, which is up to billion solar mass. However, and this one is a local supermassive black hole, which is a very famous one because we just make the first image of it, M87. So by comparing their host galaxy size, we see that the host galaxy for the massive black hole at high redshift universe is hundreds of times smaller than the host galaxy for the host galaxy for the black holes in the local universe. However, the black holes reside in them are able to grow way much faster than their host galaxy. This high redshift black hole is able to accrete to the mass billion of solar mass in the first 10% history of the universe at redshift 7.5, and this is quite remarkable. So one question to ask is that, will those high redshift galaxies ever stop growing? Is there any mechanism that can prevent the black holes to keep accreting crazily? So we know that the high redshift supermassive black hole are entirely luminous because the accretion energy because during the accretion process there's a lot of energy dumped, so that we are able to see them this far away. But on the other side, those energies liberated is also dumped into the host environment of the gas. So they're able to heat and pushing out its nearby gas, and here we already have the observational evidence that the high redshift quasar can launch strong outflow in this local environment. So this is a spectra of the quasar, and these two white wings, these two tails, is the indication that the quasar has launched strong outflow gas with speed up to thousands of kilometers per second. So in the meantime, in BlueTides simulation, we indeed are able to find those strong quasar-driven gas outflows. So this is the image of the outflowing gas that is really escaping from the host halo. And here is the histogram of the radial velocity for all the gas in the halo host. So the green shaded area is really the outflowing quasar that is escaping the black hole, which can reach velocity up to thousands of kilometers per second. And the red envelope there is the molecular gas, which is actually forming the stars. So this indicate that the agent feedback process is able to slow down the accretion process as well as quenching the local star formation. Then finally, we're going to look at the obscuration of those first quasars. We know that many supermassive black holes are obscured because they're surrounded by high-density gases. So here we plot the gas environment we plot the map of the local gas environment around the most massive black hole from redshift 10 to redshift 7. This is a single object, but different physical quantities. So this volume plots the column density NH as in different line of sight. So basically, the red area is the highly obscure direction, and the blue area is the low obscure direction. And in this column, we plot the radial velocity of in each line of sight of the gas. So the red region indicates the strong outflow direction. So we see that there's a very direct correspondence between the low column density region and the strong outflow region, which gives us a picture that the high redshift quasars are surrounded by high density gases. However, the agent feedback process can co-evolve with its local gas density field and bring strong outflow that clear the view of the quasar itself. So here's the conclusion slide that the ongoing the current BlueTides simulation, the ongoing BlueTides 3 simulation is able to cover the epoch where we are getting more and more data, and we are able to make predictions for the future for the next generation telescopes. Thanks.